Welcome to this presentation on Ziegler-Nichols tuning of PID controllers. We will state the PID control law, we will explain what tuning is, and then we will present two methods of Ziegler-Nichols tuning. Let us consider the PID controller, we call it basic design. Let the input to the controller be E of t, the output from the controller is U of t. Let k be the gain of the PID controller, tau I is the integral time, tau d the derivative time. Then the standard PID control law is given by this equation. You have proportional, integral and derivative modes. When you take Laplace transform of this, you get this expression. Capital U denotes Laplace transform of time domain signal small u. Similarly, capital E for small e. Now I can common factor this, and the denominator has tau I of s. We will generalize it as RC of s in the denominator. We will refer the numerator terms as SC of s. You have to remember this. This is the expression we will use in the rest of this lecture and also in subsequent lectures. Because we have integral mode here, when I substitute s equals 0, the denominator becomes 0. That is, the RC of s equals 0 is 0, which is clear from here. We will also see that in the discrete time case, the condition will be RC of z equals 1 will be equal to 0. We will see this shortly. In addition to this standard version, there are many modifications in a PID control law. The first one is to have a filtering action. That is because high frequency signal gets amplified because of this direct multiplication of s by tau d. Noise is generally of high frequency, so the noise gets amplified by this form of PID control law. So we introduce a filtered derivative mode, where in the denominator of tau ds we introduce this 1 plus tau ds. So when frequency becomes very large, you see that this 1 plus tau ds by n will be dominated by tau d by s, that is, it can be replaced by tau ds by n, and so these two can cancel and this whole thing can be replaced by this capital N, which is a finite number. So n is a large number of the order of 10, 100 and so on. Once again, we will denote this as SC by RC. SC is the numerator polynomial, RC is the denominator polynomial when you simplify this. Next we will take up the topic of tuning a controller. What does tuning mean? It means assigning control parameters by trial and error. For a PID controller, these are k, tau I, tau d, etc. For example, n and other parameters. Often we have to do an extensive number of simulations. It could be very time consuming. So guidelines to tune are very useful, which we will see in the next slide. Why is the word tuning? In old days we had radio knobs. Using the knob we used to tune them, so we call it tuning a controller. We will next take up the guidelines. Here are guidelines to tune a PID controller. Let us consider the proportional mode. It is the most popular control mode. Increase in proportional mode generally results in decreased steady state offset, increased oscillations. We will next take up the integral mode. It is used to remove steady state offset. Increase in integral mode generally results in 0 steady state offset, but unfortunately there could be increased oscillations. The final parameter is the derivative mode that we will consider. It is mainly used for prediction purposes. Increase in derivative mode generally results in decreased oscillations and hence improved stability, but unfortunately this mode is sensitive to noise. It is used extensively by electrical and mechanical engineers who have to deal with unstable systems. It is used less by chemical engineers, mainly because of measurement noise. I would say at this point that chemical engineers perhaps should use the derivative mode more often. In any case, PID is the most popular controller in industry. Let us now take up the tuning of PID controllers by the very famous Ziegler-Nichols method. This method was developed in 1942 during the Second World War. It is still the most popular method to tune PID controllers. It is based on a good behavior of prototype systems. This behavior was defined by Ziegler and Nichols. Of course, further tuning is generally required because most systems are not necessarily similar to prototype systems. There could be some differences. So further tuning is generally required, but the parameters given by the Ziegler-Nichols method are useful as a good starting point. Of course, there are many other tuning methods also. There must be hundreds of tuning methods, if not 1,000 tuning methods. We will take up the method called reaction curve method of Ziegler-Nichols tuning. You have to remember that this is applicable only to stable systems. What do you have to do in this? You give a step input to a stable system and get the following curve. This curve is called a reaction curve. Note down these parameters K, L, tau and so on. Okay, here is the same curve. We have noted down K, L, tau. We also find the slope here R, which is this K by tau, slope of this straight line. L is the time lag after which the system starts responding. K is the steady state gain. Remember, we give a unit step input, so K is the steady state gain, and tau is the time the output takes to reach the steady state after it starts responding. It takes tau units of time to reach the steady state after it starts responding. And as I mentioned earlier, calculate the slope of the response also. Then the PID settings are given below. They are all given here. If you want to use only proportional controller, here is the setting for K value. If you want to use a PI controller, here is the setting. The last line denotes the PID setting. You have to remember to use consistent units, especially for time. We will next take up a Ziegler-Nichols tuning stability method. So this is the second way of finding PID tuning parameters. This will work even when the plant is open loop unstable. What we have to do is to close the loop with a proportional controller and make it stable. Then you increase the gain until the closed loop system becomes unstable. At the verge of instability, note down the following: controller gain Ku, which denotes ultimate gain, period of oscillation Pu. Here we assume that for smaller values of K, the system is stable, and as K increases for large enough value, it becomes unstable. For such systems, this method will work whether the plant is open loop stable or unstable. It has to satisfy this condition. For a large enough k, it becomes unstable, and that k is denoted as Ku, which stands for ultimate gain, and the period of oscillation at that point denoted as Pu. Okay, what are the parameters given Ku and Pu? The settings are given below. This is for proportional controller, second line is for Pi, then PID. Once again, you have to remember to use consistent units. In this course, we have not spent much time on Laplace transform or tuning a PID controller. It is assumed that you already have those. Many plants already have PID control law obtained through tuning. The focus here is to discretize these. Of course, there are many more methods, possibly infinity of them, to arrive at such tuning methods. So what do? A common procedure to design a discrete PID control law is given now. Tune the continuous time PID controller by any popular technique, and hence obtain continuous time PID settings, discretize it using area based approximation or zero order hold or step response equivalent methods. We will discuss these two in the subsequent lectures. There are also new methods. Directly design the PID control law in discrete time domain and then map them into PID controllers. The method of discretization that we will discuss in this lecture will be important. There are many plants that already have continuous time PID control settings, but they have difficulty in discretizing. With a good theory, discretization becomes straightforward. There are many instances where after discretization they tune once again in the discrete time domain because of inadequate understanding of discretization method. The method that we present in this week will ensure that discretization will work, that you will not have to do too much of additional tuning. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.